and I am a product engineer at Esri on the Field Apps team. Before I get started, I would like to thank GPN for inviting me here today to speak with you. Today, I'm going to talk about data integrity. What is it? Why is it important? How can we use it to set ourselves up for success? And I'll conclude with some tips and tricks. What is data integrity? According to Harvard Business School, data integrity is the accuracy, completeness, and quality of data as it's maintained over time and across formats. Preserving the integrity of your company's data is a constant process. Okay, great. That is a great definition in theory, but what does that mean in practice, especially in the GIS space? Why is it important? We have been tasked with setting up a database for a small business survey in the county. We set up the fields we think are relevant in the database and a digital form for the county workers to survey the business owners and input the data. We're then asked to analyze the data that's been collected, including finding the average number of employees for each business. But there's a problem. We don't have a field with that data, so it wasn't collected. We're also asked for some statistics based on business type. We created a business type field as a text field, and as a result, we have different answers for almost every business. And lastly, we're asked to report on the business profits, but the directions to the county workers were unclear when they were collecting the data. So some of the collected profits numbers for the month, some for the last fiscal year, and others for the current fiscal year so far. We can break these problems down into the following categories: missing data, wrong format, and human error. How can we avoid these issues and set ourselves up for success? I'm going to use database here as a catch-all for feature classes, feature services, etc., since they all have a database of some form on the back end. When we're preparing to collect data into a database, it is important that we know all of the data that we need to collect. Think about it like we're building a house. We wouldn't just go to the hardware store, buy a bunch of wood and nails and windows and doors. We would need a plan first. How much wood do we need? How many nails? Where will the windows and doors go, and how many do we need, and what type? There are tons of questions we would need to answer before breaking out a hammer, including what kind of foundation will our house sit on? A slab, a crawl space, or a basement? Or in the GIS or database side, what kind of database or GIS file type will your data live in? Just like building a house, it's important to start with a solid foundation. Pick the database or file type that will work best for our survey. We'll also want to consult with those involved in the project. What data do they want to collect? What questions do they hope to answer? That second question may be even more important than the first. They may know that they want to collect business type information for analysis, but how are they planning to analyze that data? Should we use predefined selections of business types for easier analysis later? Having all of this information up front will help streamline the process of building our database and then our forms for data collection. Let's look at some of the tools for improving accuracy and preserving data integrity. Most of these options are going to be set up in your digital forms, but there are some that may require setting up some data in the back end, such as domains or ranges in your database, which restrict the data that can be added. Domains are lists in your database with pre-selected attributes. For example, if we have a field of colors, our domain may consist of red, orange, yellow, green, blue, violet. A user will only be able to select one of the options listed in that domain. This helps with issues like spelling errors or when we're trying to analyze data and want to group the data into pre-selected categories. Domains can be used in a form with things like drop-down lists or radio buttons. Ranges are usually used for numerical or date data types. For example, we might have a specific date range for collecting data. We can set the range to only allow users to select a date that falls in that range. So if we're only collecting data for the month of August, a user can't select a date in September or any other month. The same concept applies to numbers. If your survey assumes that a small business has 100 or less employees, then a user can't enter a number greater than 100. I already mentioned drop-down lists and radio buttons. A few other tools that may be available to us are date pickers, which show a calendar allowing users to select the date from a calendar, so it's properly formatted in the database. A barcode, which if scanned can automatically enter data into a field or fields for a user, nearly eliminating human error for those fields. Multiple select or check boxes allow users to select multiple items from a list. Again, that gives users pre-selected group of options to choose from, just like the drop-down list or radio buttons, but in this case, the user can select multiple options instead of just a single option. Overall, the less typing users have to do, the less likely there is to be an error in the data. Using tools like these can cut down on typos and other human errors. It can also help collecting, make sure that you're collecting the right data. Another tool we can use is data types. A few examples of data types are strings or text fields, integers, float or decimal, and date. Using the correct data type and field length will help ensure that we're getting the data in the correct format for later analysis. For example, if we made our business profit field a text field, we wouldn't be able to do numerical calculations on that field later on, or at least not without having to do some work on the back end to turn the strings into numbers. To save ourselves from future headaches and additional work later on, it's important to keep our data types for our field in mind while we're planning out our database. We'll also want to keep data types in mind when we're bringing data into our database from another source. What field type is the data currently in, and will we be able to properly map the fields if we were to join them or append the data from one database into another? Let's look at that question about how many employees there are at each small business again. We may think about creating a domain using a text field to display options, for example, 0 to 5 employees, 6 to 10 employees, 11 to 20 employees, and so on. This may work very well for the county workers collecting the data since it allows for collecting and displaying the data based on this range. However, now we need a way to do analysis on this data based on quantities. While the values stored are appropriate for the form, they aren't much use anywhere else. Numeric calculations could not be performed on this for analysis later, and the data would have to be translated into numbers manually, or new data would need to be collected. If we had collected the data type as a number type rather than a text field, an application could be built to display the range in which the numbers fell, but the underlying data would be accurate and quantifiable. The data can then be reused in other applications as the data as an accurate representation of the data itself and not an interpretation of itself, i.e. a range. When looking at data types, we want to make sure we are considering any possible future uses of the data as well. If we're creating a reference ID for something, and we already have 850 items, we may want to consider making the data type longer than 3 characters, as we may get to the thousands soon. If, however, It's a number that is for a specific car model, and that model only increases by one a year. 3 digits may be a safe bet. We don't want to go so small that will meet our limits quickly, but we don't want to go so large that we're taking up more space than necessary. Data types are configured to store very large numbers of characters unnecessarily can result in performance issues when retrieving and displaying that data. So you'd want to give our data types some thought when designing our databases. Our naming conventions is another place we can work on data integrity. When naming objects or fields, it's recommended that we establish some type of naming convention to avoid confusion. If everyone is naming things according to their own conventions, data becomes difficult to follow. Consider perhaps naming objects that store multiple records like tables, feature classes, shapefiles, etc., with plural identifiers, and then naming individual records or columns with singular names. For example, if we had a table that listed all the various color options for cars, we might name the table object colors, and then each record would be representing a particular color. Perhaps a column in the table would be called color name to represent the name of that color. Although there are multiple colors in the table, we do not call the column by a plural. Another consideration to make in our naming conventions is to avoid the use of any characters other than alphanumeric characters when naming objects. While some database storage systems will allow for some special characters with delimiters, others may not. If, for example, we named one of our database objects with a slash and it was brought into a URL when viewing it into an internet browser, the application may become confused and interpret the slash as being part of the URL string. So it's best to stick to alphanumeric characters and underscores. There's also rules regarding the length of some object names. So be sure to consult the documentation when naming objects to avoid hitting any restrictions or limitations. If we were maintaining a database that stored information about vehicles in our fleet, we wouldn't want to have two of those vehicles with the same vehicle identification number accidentally recorded in the database. This is a value that we know must be unique for every vehicle. We can avoid this by implementing a unique or primary key constraint on that column. This tells our database that it should disallow an entry into our records if the value already exists in that column, and that an error should be returned stating that we have attempted to violate this constraint. This helps to prevent any incorrect data being entered into our database due to some user error. If we have a column in another table that needs to reference a recorded bit of information from another table, we can put a foreign key constraint on this data. For example, if we have a table of vehicle drivers, and that table includes the VIN of the vehicle that the driver is assigned to, we would want that VIN number to match the one of the values in our vehicle table. This would prevent a user from entering a VIN for a vehicle that doesn't exist in our fleet. The design of your data is something you should give considerable thought to. Restricting the creation and changing of data structures on the fly is a practice that should be encouraged. Otherwise, your data may not become disorganized, but the integrity may come into question. Before I mentioned the foundation of a house, what are we going to build our data on and how will we access it? Let's dive a little deeper into that foundation. Now that we know our data represents, we have carefully designed the structures and the rules that govern the storage of the data within those structures. We turn our focus to the architecture and storage for these data structures. We can start by doing an inventory of our current architecture, determining what meets our needs, and then look into building upon or expanding where needed. Determining what we need for storage and architecture requires focus on many things, but the main areas we'll take a look at are where our users are located, how they are consuming our data, and how and where we store the data structures. The combination of these three items will dictate our requirements. Are our users, where are our users located? All connected from the same office building or group of buildings, or are they distributed? Are they spread across multiple states in other countries? Are they in the field? Are they outside of our networks? Will they be connecting through some sort of middleware like Citrix? For those unfamiliar, Citrix is basically remote desktop and other virtualization software for working remotely. Next, we need to understand what our users will be doing with the data. Will they simply be viewing this data in a read-only capacity, or maybe running a biannual report off of the data? Are they doing heavy day-to-day editing workflows? Maybe it is a combination of all of these things. The quantity and frequency of communication can be done by users with the data may influence the next piece of our architecture, the data storage location. A common data storage technique is file-based storage, such as a shapefile or file geodatabase. This method of storing and consuming data has been widely used for decades and can be a viable option for data storage today. But is it the best option for us? Perhaps a more centralized repository of data rather than files scattered across folders, file shares, and various machines is a better fit. Perhaps a relational database system such as Oracle, Microsoft SQL Server, or Postgres that include native spatial data types would be a better fit. Maybe an enterprise geodatabase built on top of one of these relational databases is exactly what we need. Whether we decide to centralize our data through the use of a single file share system or through a relational database management system or enterprise geodatabase, we need to determine where we are going to place this repository. Will we store it locally in the same building as our users? Will we store it on the network, but perhaps in a different state, maybe across the world? Perhaps we'll store it in the cloud or a data center, maybe in Amazon S3, or perhaps in a cloud database like Microsoft Azure. The initial answers to these questions begin to inform our architecture needs. Every different combination of factors across these three areas yields a different recommended practice. Let's assume we decided that we want to have a central repository of data stored in an enterprise geodatabase in the cloud to avoid having to buy and maintain our own server hardware. We have offices in New York and California, and our users perform numerous edits every day from our internal network at both locations. We choose to host our data in the Ohio region as it's in the middle of the two locations. This setup will inevitably result in extreme performance lags due to the architecture. Communication between a server geographically distant from the users. Connecting to a cloud-based database should be done from users within the same cloud, or there will be severe performance issues. The same would occur if we hosted a file-based data in the cloud like Amazon S3. So how do we alleviate this? We need to be flexible in our planning. We can either move our database centrally, investigate using some sort of middleware, or adopting the use of services. Each of these has their own stipulations, so we need to determine what is going to best serve us in the work we need to accomplish. If our workers in New York were simply reading the data for reports twice a year, while all of the workers in California did edits, maybe storing the database on premises in California wouldn't be so bad. Sure, those 2 times a year accessing the data from New York would be slow and somewhat painful, but maybe that's something you could live with those 2 times a year. But it's possible that it wouldn't be cost effective for daily editing workflows. Sometimes we can get caught in thinking that we need to choose one specific way to store all of our data, no matter what its use is. When in truth, choosing different options for different scenarios may well be the best course of action. You may drive a hybrid vehicle every day to help protect the environment. But if your goal is less emissions, you probably wouldn't want to use that hybrid to move to a new house. The number of trips you would need to make to bring all of your belongings from one location to another in your hybrid would likely exceed the emissions of a single use of a moving truck. One has environmental benefits for everyday use, but it may not be an optimal solution in another. In short, you want to consider a collection of factors when making your decisions about storage and architecture. Not every data need use is the same, and therefore a hybrid solution may be required to handle different projects efficiently. In keeping with our house analogy, we talked about building the house and the foundation, but now that we have our house built, how do we care for it and maintain it? We've got buy-in from our users, and we're ready to begin operations. At this stage, it's not unusual for folks to assume the design is done and it's safe to walk away feeling accomplished. To ensure that none of our hard work designing and architecting the solution goes to waste, we need to take the time to plan out the care and feeding of our data. We want to protect our data structures and the data stored within them. A great way to do this is to implement a change management plan. Without a plan in place, ad hoc changes to the data structure can become commonplace, and the authoritative nature of your data begins to come into question. We want to make sure that not just anyone can make changes to our data structures, such as adding new columns or deleting old ones. We also want to make sure that those who do follow a specific outlined process when doing so. Another important part of your data management plan is to consider is avoiding the unnecessary duplication of data. At one point, I worked with an organization that used a file share system for storing their data. This one share had hundreds of gigabytes of file data consistent of dozens of copies of the same shapefiles copied over and over and renamed for use on specific projects. Every time a new project came along that required the use of data within that shapefile, with the addition of some extra attribute fields, the data was copied, the data structure was altered to include the new information, and renamed to tie to the new project. Over time, the authoritative nature of the data became questionable. Which copy had the most up-to-date and accurate data? After a number of years of this practice, someone had to be hired to go through all the copies to assimilate the data and determine the accuracy. We don't want our data to suffer the same fate. So it may be wise to implement processes and guidelines to restrict the creation of copies of data. Who here has had a change occur in their data and no one knows how it happened? We don't only want to protect the structures of our data, but also the quality of the content through quality assurance and quality control processes. There are various ways to do this, but one way is to make use of versioned data workflows available in enterprise geodatabases. It is
Hey
possible,
there.
yeah.
I'm sorry, I don't mean to stop the flow of your presentation. We're not seeing any text on your slides.
Oh, yeah, no, there is no text.
Okay, I just wanted to confirm
Yeah,
before you continued on. Thank you.
yeah, no problem. Okay, thanks. All right, I guess I'll just jump back right in. I'll start at the top, well, of this slide anyway. There are various ways to do this. but one is to make use of the version data workflows available in enterprise geodatabases. It's possible to keep the authoritative source of the data safe while still allowing advanced geodatabase functionality and allowing multiple users to conduct editing concurrently. Once all these edits are made to versions of the data, these changes can be reviewed for accuracy and then accepted and merged into the authoritative data source. Another option is geodatabase replication. This functionality is built on top of the versioning architecture and allows a copy of the data to be edited separate from the source data. The data can then be merged back into the source. This can be a viable option for our hypothetical scenario spanning New York and California. One reason one location has the authoritative data on premises, and the other has a replica of the data where the edits are made. At scheduled off-peak times, these can be reconciled with one another and the changes can be brought to both locations. If you adopt either of these processes, make sure you understand them thoroughly and the maintenance required to keep them running smoothly. The last piece we need to focus on is the overall health of the data. We need to manage the data and data structure storage. If we're utilizing versioning and replication, we need to make sure that we are reconciling these regularly to avoid causing performance degradation. While the benefits of using these structures are many, the incorrect use can lead to performance issues and other problems. If we implemented versioning but never performed any of the versioning maintenance, by the time we start to see performance degradation, there may be millions of edits in the versioning tables, and the administrative tasks to reconcile these edits could result in running tools for hours to days to complete. We also want to be sure to keep our storage hardware and software up to date and manage user access to our data. When we choose to host our data internally, the lifecycle of the data and system maintenance are typically handled by an individual, typically a database administrator. This is often the preferred approach for the data that requires systematic vetting processes before exposing it as service. Enterprise geodatabases also allow low-level and fine-grained control over database details, such as database indexes and statistics, exactly because of the user-managed nature of the database. For larger data sets, they're also subject to heavy performance and sensitive inquiries. Many database administrators may prefer to keep them in a user-managed system to maintain tight control over these kinds of details and executive backups. But another option is to allow ArcGIS to manage these things. I promise not to be an Esri commercial, but I did want to mention that option. ArcGIS managed or hosted items can be imposed to control whether or not an item can be viewed by specific members, deleted, edited, synced, shared, exported, and more. Note that your storage choices for your databases can always change. You can choose to create hosted data out of your data that was formerly stored in your enterprise to your database, or you can export your hosted data and incorporate it into your enterprise geodatabase. The choice does not have to be permanent and can be adjusted based on your ongoing organizational needs. When considering how and where to store your data, it is recommended that you understand the format, the characteristics of your data, and how you want to interact with it. With solid data design, architecture, and management, you can leverage your data in multiple ways across multiple projects to maximize efficiency, performance, and accuracy. Now for some tips and tricks. I did talk about these first few before, but it bears repeating. When you have users collecting or editing data, use the tools available to you to minimize the amount of typing they need to do. These include drop-down lists, radio buttons, select multiple, and any other tools you can use to minimize typos and other human errors. Along those same lines, use ranges when they make sense. If your field values should fall between 5 to 50, set a range so you don't get data outside of that range. And add data types and length. They're important. Does that text field really need to be 255 characters for that city name? Or can we drop that down to 20 or 30? And does it make more sense to make a field a text field or a number field? Will we be doing any calculations on that field, or is it something like a zip code, which is a number, but is more likely to be concatenated as part of a string than used in any kind of calculation? Contingent values are another great way to protect your data integrity. Contingent attribute values are a data design feature that allow you to make values in one field dependent on the values in another field. We talked earlier about domains and ranges, which restrict the data entry to a set list of range values. Contingent values extend this model by making your choices for a value in one field, constraining the domain's values that are placed on another field. So for example, if we're collecting data on our fleet vehicles, we can add the contingent values on there and maybe we enter Toyota under the make field for the vehicle. In the model field, the domain would be constricted to only Toyota vehicles. So you wouldn't end up with a 2024 Toyota F-150 somewhere in your database. Data validation and validation tools can be set up so that users will receive an error if they try to submit invalid data. For example, if a user is adding a new gas line to the system and forgets to add a meter at the building, they'll receive an error message letting them know that the data is missing. Once they add the data, they will be able to submit the data successfully. Editing or feature templates can take advantage of default attributes and preset configurations. Let's go back to that gas line from the last example. By setting up a group template, when a user enters a new service line, they select the template, tap on the existing gas main, which will add a T to the line. Their next click will add a valve and connect the two by drawing a service line. And with their third click, they'll add a meter at the building or house, which again will be connected by the service line. Now that we have all the components needed for that new service line, some attributes may be filled in already with some default values such as manufacturer or other construction material information. The rest of the attributes can be filled in by the user and submitted. This next one I bring up specifically because I work on the mobile side of things, and it has to do with device accuracy. If you have users collecting data out in the field and the GPS accuracy with your device is extremely important, such as for underground assets, there are tools and settings available to make sure that one, the person taking the GPS reading from the actual location and not phoning it in from the Dunkin' across town, and two, that the GPS readings fall within a certain accuracy threshold that you set. For example, if you set the GPS accuracy to plus or minus 3 meters, and the user tries to capture the point with the accuracy of 10 meters, then they would need to wait for the device to reach that plus or minus 3 meter accuracy before they can capture the data. And lastly, Arcade is another tool available to help with data collection and editing. Say that you have users in the field collecting data on code enforcement violations. If they were to add a feature inside of an existing parcel polygon, you can use Arcade to fill in property information such as the owner's name, parcel ID, and physical address. This not only helps with data integrity, but also speeds up your data collection process. Automation tools such as Python are great for repetitive tasks and calculations. If you have lots of data entry happening daily, and part of that data entry involves complex or even simple calculations, you can set a Python script to run nightly so it completes those calculations for you, freeing up time for those entering the data and protecting your data integrity by knowing those calculations are going to be done correctly each and every time. There are a number of tools and processes available to help you every step of the way to create and maintain healthy and reliable data. Starting with creating a database schema, which will house all of your data needs for that particular asset or project, to using the right data types. After you create your database, you will populate it with the data using tools that help you keep your data integrity. Once you have populated the database, you will keep it healthy with the data or schema is edited by enforcing change management standards. Data integrity is an integral part of the work of the life of your data. Not only is it important to keep your operations running smoothly, but can also save you money over time. Having accurate data will allow management in your organization to make better decisions based on better data. Questions can be answered faster, easier, and more accurately when using complete and accurate data. And you won't have to find yourself in a position where you need to hire someone to sort through duplicate copies of your data to find the most up to date information and weed out the good from the bad. I started with this quote from Harvard Business School, and I'd like to end with it too. Data integrity really is a constant process. It's a standard to reach for every day with every new database and every new bit of data. Thank you so much.
Thank you, Kerri. Your presentation was excellent. We'll go ahead and stop the recording here and then open up things for questions and discussion, if that's okay with you.
Sure.
Okay.